Hello students, welcome back. We just completed section 1 of this notebook and it was highly computational. In terms of theory, we didn't do too much. We talked about a linear operator, a linear map from one vector space to itself. Eigenvectors and eigenvalues for linear operators, they may exist or they may not. In any case, if they exist, you're going to get L of v equals to lambda v, where v is non-zero. If we do have eigenvectors and eigenvalues, how do you find them? We find them from characteristic equation. Roots of the characteristic equations are eigenvalues. And once you have eigenvalues, you can set up systems of linear equations to find out eigenvectors. And then, one more thing. And then, here. And then, set of all eigenvectors for a given eigenvalue form a vector space, a subspace, if you take a union with a zero vector. We call it eigenspace, and you can determine eigenspaces for given eigenvalues by taking one eigenvector or more if you have higher dimension, and then taking a linear combinations of those. We went through all those. Okay, the next topic we have to do is diagonalization, and it has something to do with this example here. If you have a diagonal matrix, then what are the eigenvalues? It turns out the diagonal entries are the eigenvalues. There's nothing else. We'll prove it, but the proof will be in the third section, or we may have to postpone it even further. But the key here is now how do you find these? And how do we use those for further computation? That's what we are up to. So let's have a brief summary here. This is where we're headed. For a n by n matrix, in some cases, and that's rather difficult, in some cases, under a suitable condition, we can find a basis that consists of eigenvectors only. And if we do that, then simply take the coordinate expressions of each eigenvector, x1 in column, x2 in the second column, and so on, and xn in the last column. Then this expression T inverse AT turns out to be the diagonal matrix with all those lambda 1, lambda 2, and so on in diagonal entries like this. It turns out lambda 1, lambda 2, lambda 3, all these eigenvalues here, this diagonal matrix turns out to be T inverse AT, where the T is given by all those eigenvectors, first column, second column, and so on and so forth, the last column. This kind of process is called a diagonalization. Now, why is this diagonalization so useful? That's because we want to do something like this. How do you calculate a to the nth power where n is really, really big, like 1,000 power or something? Or sometimes we can consider infinite powers as well if we have power series. Yeah, okay, let me write it in that fashion. Maybe that's a bit more dramatic, so let's go back to this. So let's express it as a power series, all right? So n is moving from 0 to, oh, excuse me, no n. Typically, I'm using n for dimension in this course, so let me use something else. Okay. Let's suppose we are looking for this kind of expression. It's a power series of matrix A, so a to the k power, where k power can get really big. And even for supercomputer, it can't handle this precisely because this k power goes to infinity. It can handle, of course, approximation, But even so, it's not really efficient. So how do we handle this? A good way to handle this is doing this. Instead of A, let's see. D is equal to T inverse AT. Okay, in that case, A is gonna be T D T inverse because of this. Just flip this T inverse to the other side and T to the other side. And then, what is this? T D T inverse to the K power. That's basically this times, let me copy and paste this whole thing. Okay. Okay, that's enough. Okay, it's basically this kind of computation. And then please note that T inverse T, they cancel each other out because they become identity. And T inverse T cancel each other out, they become identity. T inverse next T, they cancel each other out. Everything in between cancel each other out, and what do you get? T times D to the nth power, K power, excuse me. This is what we get. And D to the K power is actually easy to calculate because this is diagonal entries. So all I have to do is take the K powers of all these diagonal matrices. So basically what we have is this one to the K power, this thing to the K power, like this. So we can handle this kind of thing. All the powers are just T power and that. And let's go back here. It is the same as T and then these are just diagonal entries. So basically we have just power series expression in here for lambda 1. And then exactly the same thing for lambda 2. And then exactly the same thing for lambda n, the last entry. And then what are these? These are just power series expression for real number arithmetic. So we can handle it. For example, if we have exponential expression, so for example, if 1 over k factorial like this, then this is nothing more than 1 over k factorial goes over here, goes over there, goes over there, all right? And then what are these? This is exponential. So this is nothing more than t, okay, I'm gonna run out of space here. So let me continue here. That's gonna be equal to t and this one over here, as a matter of fact, exponential. Lambda 1. That's for lambda 2. And Okay, let's align the equation like this. So basically what happens is something nearly impossible to calculate can become something we can calculate rather easily. As a matter of fact, we know an awful lot about the exponential function. Now, if you have this matrix expression, how to calculate this using kth power with infinite power? We can't do it. Even with supercomputers, we can't do it. We can only get approximation, which is probably not a good approximation anyway. But if you use this kind of argument with diagonalization, then you can get precise answer. By the way, taking the exponential of a matrix is extremely important technique in differential equations. I don't know whether we'll actually get there in differential equation 1, math 3410. If there's anybody taking differential equation 2, definitely we will cover this kind of thing and a whole lot of other things as well. But I don't know whether we can actually get there in diff equal 1. Still, for linear algebra, we can handle it, and we will do something like this. No, I'm not asking you to do all these things, reproducing all these things. No, we are not doing that. We are doing just taking transition matrix T. How do you find it? By taking eigenvectors as columns, and so on. And then just exponential of diagonal, and that's about it. Okay, I guess we have enough time, just enough time for one example problem without any proof. All right, here's a 3 by 3 matrix, and find the diagonal matrix D and the transition matrix T such that D is T inverse AT. Or equivalently, A is equals to T D T inverse. These two are equivalent. All I have to do is flip this T inverse to the other side into T, and then this T to the right hand side into T inverse, and that's what we get over here. So these two are equivalent. Okay, all right. How do you do that? Diagonalization theorem said we're taking eigenvectors as columns like these. So that's the matrix T, which is called transition matrix. Okay, let's do it. Let's see, do we have full answer here? Okay, all right. Let's find the eigenvalues. Determinant of A minus Ti is equal to 0. Characteristic equation. So what is this? Determinant of minus T times 1, 0, 0, 0, 1, 0, and that is equivalent to what? Determinant of, now I'm going to go to that thing, exactly the same thing except minus t in principal diagonal, minus t, and then minus t. That's it, isn't it? So experienced students will go to this step directly. Exact same matrix A, but minus t minus t minus t in principal diagonal. Take the determinant, set it equal to 0, and you're going to get a polynomial equation. It's rather tedious, so I'll show you this. take the determinant, and then what choice do you have? You have to expand and do some work. Assuming you do all that, you're going to get these three eigenvalues. T equals 1, minus 1, and 2. Those are the roots. So those are the eigenvalues. 1, -1, and 2. Alright, for these eigenvalues, 1, -1, and 2, you have to find eigenvectors. Okay, 1, -1, and 2. So 1 times this, -1 times this, 2 times that. We have these three systems of linear equations. How do you solve these? Oh boy, it's going to be a tedious work because each system of linear equation is, well, each system needs some tedious work, and we have three of them. So I'll take a shortcut. I'll just show you the first answer here, blue one here. And then this matrix times xyz is 1 times that. So matrix computation here. And then I usually flip these right-hand side, subtract over, and then keep the right-hand side equal to 0, and then make it into a homogeneous system of linear equations. And apparently what I did over here is some elimination. In the end, I got this. Z equals to 2x, and then y equals to -3/2 x. All right. So what do you have? XYZ is gonna be x. Let me see. Let me put one extra step. X and then minus 3/2x, and then 2x. I could have gone like this, but if I do this and then plug in x equals to 1, then what do you have? We have fractions. So instead of plugging x equals to 1, I decided to plug in x equals to 2. So plugging x equals to 2, then this becomes 2, all right? And then 2 times that, so I eliminated the denominator, -3. And 2 times 4, we got that. So from here, instead of just taking these and then x equals to 1, I decided to take x equals to 2 for the similar expression. You can do something similar to the red system, just solving a system of equations. Green, again the same. So what we have first eigenvector, 2, -3, 4. That's the first column. And then second eigenvector, 1, -1, 1, second column. And the third eigenvector, 1, -2, 2, third column. And there goes the diagonalization. 2, -3, 4, first column. 1, -1, 1, second column. 1, -2, 2, third column. So here is a diagonalization. Diagonal matrix D is equal to T inverse AT. Or equivalently, the A is T D T inverse. And then finally, if you want to calculate exponential matrix with one T D T inverse, so T exponential of D T inverse. So what do you have? T inverse there, but we have just exponentials of these eigenvalues. So direct computation was impossible, but with diagonalization, we have this beautiful expression. Here's a Mathematica program for that. Let's see, how does it work? Oh, what a mess. Never mind. Let's stop here.